Welcome, students and viewers, to this third iteration of this medical imaging system lecture series regarding tomographic techniques. The first two lectures, uh, I briefly talked about the basics of computer tomography, covering the basics of X-ray and X-ray radiography, talking about the working principle of X-ray and the basic different components of a typical X-ray imaging system covering the different X-ray generations, as well as talk briefly about the radio contrast agents and its adverse effects. So in this lecture, I'll briefly talk about the state-of-the-art techniques or the state-of-the-art imaging tools or imaging parts of imaging instrumentation that are used or different types of CTs that are used in the clinical settings for both clinical as well as research motivated applications. So again, I am Arindam Chakraborty. Welcome you to this medical imaging system lecture. So this is uh, a very typical example of a modern day uh, imaging system, CT imaging system, pardon me. So this is a Siemens system that was developed in 2021. So as we can see here, this is basically is the whole gantry which houses both the X-ray source as well as the X-ray detectors, as well as all the other components like the spatial filtering, the X-ray collimators, all other digital image processing parts. And this is the bed which where which houses the patient, and this is where the patient X-ray beams and the source it rotates across it and takes the image. This is a very recent one. So there are other important aspects that are used that the system that are used in these recent day CT systems that I'll just discuss in the following slides. So the first thing is that when coming to the modern day CT system, uh, there is something known as a single as well versus a multi-detector CT. So what is a single, as the name suggests, what is a single detector CT? That is basically which has a single slice that is generated per 360-degree scan. So when the detector and the uh, uh, X-ray tube, this entire couple covers the in 360-degree around the patient, there is only one slice that is generated, and this is a single detector system. So there is only one detector array. So roughly we can assume that a detector array comprises around 600, sometimes 800 single detectors. And modern day detectors, they have multiple detector CT. So we call it MDCT. So MDCT has multiple detector arrays. So as we can see, probably around 4,000, 5,000 detector array in, if you can recall from my previous lecture in the fourth generation CT. So this multiple detector array allows for the acquisition of multiple slices per 360-degree rotation of the X-ray source. So as we can see from this slide, from this image rather, I'm sorry. So there are two essential difference. First is that the single slice, apart from that, the single slice is generated from a single detector array, and multiple slices can be generated from a multiple detector computed tomography system. Apart from that, the single detector array covers lesser lesser area as compared to multiple detector based CT scan, which covers a larger area, because now the fan beam is much wider, as well as the number of detectors that are present there, that spans across a larger area. Therefore, the first and the most important advantage of this detector array is that the single detector array has lesser surface area coverage, while the multiple detector based CT has wider uh, area coverage, which again causes less radiation dose because the scan time can be reduced. Since this is because if I have to scan a larger area and my the area that is being scanned through the X-ray is already very small, so I have to scan for a longer period of time. In contrast to another CT where the X-ray beam covers a larger area, therefore the scan time is reduced. Again, like I said, the collimator decides the slice thickness or the slice width in case of a single detector array, while the collimator covers the beam width while we talk about the multiple slice CT systems. So, for example, like here the one I said that the higher, so since there are multiple detectors available, the slice thickness can be reduced. It can be understood intuitively that the slice thickness can be reduced and number of slices can be increased as well per rotation. So what does that mean? So probably there are several terms that are used, that is a 64 slice CT, one 500 200 slice CT. So 64 slice CT means that it takes total 64 slides of a certain thickness, which is almost around 0.64614 millimeter thickness, that are obtained per 360-degree scan. So once this entire uh, this X-ray source covers this entire 360-degree, the detectors captures total 64 slices of a certain thickness, which is around 4.0.6 millimeter. So this thin slices allows for higher temporal resolution as well as better visualization of the internal structures. So a four slice, like discussed in the previous slide, a four slice MDCT was introduced. So basically, four slice MDCT means of it takes four images or four slices per 360-degree rotation of the X-ray tube around the patient. That was introduced in around 1998, while a 64 slice CT, that is uh, MDCT, was introduced in 2004, that has a slice thickness of around zero point 0.6 millimeters. So therefore the beam width, as we can see here, so these are all the slices and they have a slice thickness of zero point 0.6. Therefore the beam width is around 40 millimeter. In the modern day, there is already uh, clinically available CT scan or MD-CT scans are there, which can acquire as high as 320 slices in a single rotation. That means a 320 slice MD-CT can acquire 320 slices in a single 360-degree rotation of the X-ray tube around the patient. So this shows the pace at which this modern CT imaging is uh, going. That can, and what are the structural intricacies that we can visualize through through these imaging modalities. Now there is another important thing, that is a single slice versus a multiple slice CT. Unlike the previous one where we talked about a single detector and a multiple detector CT, this one is slightly different. This is where the single slice and the multiple slice CT. If you can recall, the first or the second generation, they generally produce a single slice after a single scan. So in case of a single slice, we can see from this image is that the slice thickness or the slice width is equal to that of the beam width. Since there is a single detector, the detector width is equal to the beam width, that is the slice width, and therefore the collimator can the collimator thickness basically dictates the thickness of the individual slices. While in case of multiple detector MDCT, we can see there are several slices. So the collimator, the beam width, collimator essentially influences the beam width or modify the beam width, and this is a the beam width is nothing but the multiplication of the slice thickness as well as the total number of slices. So again, the we can see the beam width is equal to the width of the individual slice since a single detector is used, while in this case, and the collimator width is nothing but the slice width, while in this case the collimator width is equal to the beam width, and the beam width is a product of the individual slice thickness and the total number of slices. Like I was saying, so if we have a n slice CT machine like the 64 slice, if we consider an n slice CT machine that can that can generate n number of projections per tube location. That that is a very important concept. So a 64 slice CT creates 64 number of projections per tube location, and it can create a total 64 number of cross sectional slices after a 360-degree rotation of the tube. And as I was saying, the beam width, which is this one, is nothing but a product of the number of slices that are present multiplied by the slice thickness or simply the detector width. This is a very important concept that one needs to remember. And now another very important one is the something known as a spiral computed tomography, or sometimes also known as a helical computed tomography. So we can say it as a fifth or sixth generation computed tomography if we continue along that generation one that I taught that I discussed in the last lecture. So we can consider this as a fifth or sixth generation of CT. So from the image, we can see that there is some means where the X-ray basically covers the entire person in a helical path. That is why it is known as a helical or a spiral CT. So why it is? Because this is the bed where the patient is lying, and the X-ray essentially covers the patient in a 3D manner, that is in a helical manner. So, in a simpler words, a spiral or a helical computed tomography is thus where the source and the detector travels along a helical path relative to the object. So, if I consider this is where the source and this is where the uh, detector lies. So, this source detector essentially travels across a helical path in relative to the patient. So, with the helical CT, the basic concept is that apart from the source and the detector array, they move, they are rotating. The patient is also being moved through the rotating X-ray beam and the detector set. That is, along with the X-ray source and the detector, the patient is also being moved at a certain pace. So, from the perspective of the patient, the X-ray beam of the CT, it follows a helical path. So if we can intuitively think that the X-ray beam is moving and the patient also moves in the perpendicular direction, so it traces a completely helical path. The patient is moving in this direction and the X-ray is moving in this direction. So overall, it follows a helical path in relative to the patient. So this helical path, what additional benefit it provides? This helical path generates a three-dimensional data set which can be reconstructed into several sequential images for generating the 3D structure. So what is the basic difference as compared to fourth generation or third generation CT that I discussed? Here, not only the X-ray source and the detector that are being moved, the patient lying in the bed, that is also being moved, which is perpendicular to the movement of the X-ray source and the beam. Therefore, the X-ray beam follows a helical path, which results in a three-dimensional data set. So as we can see from this image, so this is the X-ray source, the X-ray and the source, and since the patient is continuously moving in this direction, so this path essentially rotating across the patient follows a helical pattern. And the important thing when coming to this spiral or helical computed tomography is the beam trajectory characterization is the pitch. So what is the pitch? Is basically pitch is equal to the tape distance d that the table is being what should I say? The table is being fed directly, or the table is traversing and along the scan range over the gantry of rotation to the collimator section. So this pitch, when the pitch is greater than 1, that means the radiation dose for a given axial field is decreased compared to conventional CT. So at high pitch, however, there is a trade-off in terms of noise that I will discuss. So the pitch is nothing but this distance multiplied by the collimator, the beam width, the collimation distance that has been provided by the collimator. Now, since the noise that I was talking about, because the patient is intentionally being moved through the gantry while there is the scanning is in process, it generates a motion artifact. However, there are computational methods which is known as Z plane interpolation or simply Z interpolation, which specifically developed to minimize this motion artifact by managing the spiral data set and eliminate this motion artifact. So what happens there basically is nothing that for any image that is positioned along the Z axis of the patient, this Z interpolation method restructure the spiral data to fit it in a single plane so that the back projection or the convolution method algorithm can be applied. So what are the important thing? Important thing being the pitch, as well as there is the some sort of motion artifact. So motion artifact are generated because the patient also is being moved along with the X-ray source or the detector array. But there is a specialized algorithm known as Z interpolation, which manages this motion artifact, reduces this motion artifact by restructuring this spiral data to fit it in a single plane so that the typical reconstruction algorithm like the convolution or the back projection algorithm can be applied. Now, coming to the another important one that I briefly touched upon in the last lecture, that is known as a slip ring technology. So what is a slip ring technology and why it is particularly important? For that, we need to know that the older generation of CT machines, like I said, there were wires involved for providing the electrical uh, currents or other forms of energies, or taking the data from the detector to the computer system. So they were limited by this wire twisting or this wire misalignment. So in between, these systems have to stop working for the wire for aligning the wire or de-twisting the wire. Since this X-ray source and the detector used to rotate, the wire misalignment and the twisting of the wire was a unavoidable circumstances that they have to face. So the modern city uses something known as a slip ring to get rid of this wire misalignment or the wire twisting or tangling of wire. So slip ring is nothing but a electromechanical device that transmit power or electrical signal or any other signal from the stationary to the rotating part of the CT machine without the need for a wire. So it basically eliminates the need of a wire so that the rotation doesn't cause any misalignment, the rotation doesn't cause any other problem relating to the wire. And how it does, it basically transmit the power or electrical signals or other analog signals from the stationary part of the gantry to the rotating part, that is either the X-ray detector array coupled with the X-ray source or the X-ray source itself if we consider the fourth generation. So they are nothing basically electrically conducting brushes and generally made up of silver or graphite. So there are three types of slip rings. One for providing high voltage power to the X-ray tube for generating the X-ray, for charging the cathode to emit the X-ray. One slip ring is used. Another is for providing the gantry with a low voltage for the rotation. Another is for transferring the of digital data from the detector. So what does a slip ring technology perform? So it basically eliminates the necessity of wire. How? By transmitting power or electrical signals from the stationary part of the gantry to the rotating part, thereby for reducing the wire related problems, wire related misalignments. And they are basically electrically conducting brushes made up of either silver or graphite. Now another important aspect that is used these days that is known as, which is very proprietary technology and used quite a few these days, are known as a dual source X-rays. As we can see here, a dual source X-ray is nothing but there are two different X-ray sources are present, which are almost this detector arrays, they are almost 90 degrees apart. So a dual source CT is equipped with two X-ray tube and there are two detector arrays that are almost 90-degree apart. So what are the advantages of this in compared to a single source X-ray? First is the high temporal resolution, particularly for cardiac imaging, to better capturing the thumping action of the heart or the systolic diastolic action of the heart without the employment of any beta blocker. So this is a very unique advantage. Another one is the low radiation dose, particularly for the obese patient, as since there are two X-ray sources, so the number of slices are rapidly increasing as compared to a single X-ray source, and there is a quicker acquisition with a shortest breath hold. So this is the image that I have gathered is with the help of a Siemens proprietary technology. So they have this dual X-ray source CT, which mainly finds its application in terms of cardiac imaging, as I say, because the temporal resolution is particularly very high as compared to single source CT, single X-ray source CT, and this temporal resolution helps in better capturing the thumping action of heart or the pumping, the systole diastolic action of the heart without the introduction of any beta blockers. And another important one is the application of dual energy CT. Unlike the dual source one, there is dual energy CT. To understand the dual energy CT, we need to understand the basic energy spectrum of a CT. So energy spectrum of a X-ray, I beg your pardon, I'm sorry. So an X-ray is generated in that tube in two ways. One is known as a Bremsstrahlung, another is a characteristic spectra. So here this continuous one is basically the X-ray that is produced through the Bremsstrahlung mechanism, and this sharp high energy peaks are nothing but the characteristics X-rays. So dual energy X-rays, or sometimes known as spectral CT, I mean dual energy CT, DECT, sometimes known as spectral CT, they are fairly new technology, and recently they have been approved by the FDA in the United States for clinical applications. So they use both normal X-ray along with a less powerful X-ray to take images. So generally the X-rays that are used have the energy of around kilo 140 to 150 kilovolt. So there are two pictures that are taken at the same time at different energy levels. As we can see here, either 80 or 140 kilovolt, 100 or 140, or sometimes 70 or 140 kilovolts. So this gives this extra addition of a second less powerful X-ray source, gives DCT an additional advantage over the conventional CT. Again, this is most commonly used for cardiovascular imaging, particularly during the interventional techniques such as angiography. And this is a typical image. So this is uh, higher X-ray, I mean higher energy X-ray, followed by this lower energy X-ray, and this is the overlap region. So this gives a better visualization of the overall system with a relatively better temporal resolution. And there are two more interesting aspects which I won't be covering here, but for interested or highly motivated individuals, I would suggest to learn a bit about the portable or mobile CT, or something known as a photon counting CT or PCCT, or you can contact me in my given email address and we can discuss about it, or if you have any queries. I'll finish my lecture here. Thank you for your participation.